Hello, everybody, and welcome to this week's Astro Coffee Hangout. We're actually calling it the Afternoon Astronomy Coffee Hangout. My name is Tony Darnell, and I work at deepastronomy.com. Well, I actually own deepastronomy.com. And this is a hangout where we are trying to give you a glimpse into what it's like for astronomers to meet every week, to get together, to kind of over coffee to discuss some of the latest research that has come out amongst their colleagues. And we want to give you a glimpse into that world. And so today, Carol has set us up a really nice hangout where we're going to be talking about an interesting gamma ray binary system. It's called LMC P3, and it's an extremely rare object, of which there are only about 4 or 5 of them known so far. And that was discovered in the Large Magellanic Cloud. And gamma rays, for those of you who don't know, are extremely energetic light. In fact, they are the most energetic light that we can detect in the electromagnetic spectrum. And we're going to talk about all of this and get into more detail as time goes on. But I wanted to welcome you all to another one. And and let me introduce my co-host. Her name is Dr. Carol Christian. Hi, Carol. Welcome back. It's good to see you.
Hey, how are you?
I'm doing good. Doing good.
Good to be back on afternoon coffee.
That's right. So we set this up, and we're going to be talking a lot about gamma rays and what it's like to be in a binary companion of these things, something very rare. But I want to differentiate something between this and, say, a gamma ray burst, and we'll go.
Wait. If I may interrupt, which I will, which is my.
Which you did. So go ahead.
So first, I want to thank the American Astronomical Society and the American Astronautical Society for endorsing and giving us some moral support for the Hangouts. And also, I know Tony is going to explain to you how to interact with us, but I just want to make sure that the 2 AASs are acknowledged, because I personally really appreciate that they are supporting this effort.
Thank you. I was going to get there.
You're welcome.
We got there sooner. So there we go. Okay. So we'll talk about gamma rays here in just a little bit. Before I introduce my guest, let me tell you how you can interact with us, since Carol has gone there now. So we will, there's two main ways you can do it. There is the main, if you go to deepastronomy.com/live, I have a chat client set up there right now where people can log in and interact with us. Lots of people are already doing that now. So there is people, that's the easiest way to interact with, because I'm monitoring that. The second way is by using the hashtag AstroCoffee, and I'm going to make Carol big because in her lower third it says it right there, AstroCoffee. So that's on Twitter. I'm looking at that as well. So those are 2 big ways you can interact with us on the Hangout. So we hope you'll do that and learn all about gamma rays and gamma ray binary stars, as well as how this research has come about. Now, today, as I mentioned, this particular Hangout is about a relatively rare object that was discovered in the Large Magellanic Cloud, and we have members of the team that recently put out a paper that described this system, and they're going to share their research with us now. So joining me is the lead author on the paper, his Dr. Robin Corbet. He's a senior research scientist at UMBC, working at NASA Goddard. Hi, Robin, welcome. Also joining me is Professor Malcolm Coe. He is the professor of astronomy at the University of Southampton, where it is now the evening. Thanks for staying with us, Malcolm.
I'm staying awake. It's okay.
Yeah, thank you. Also joining me is Dr. Laura Chomiuk. She's an assistant professor at the Department of Physics and Astronomy at Michigan State University. Hi, Laura. Welcome.
Hello.
And also finally joining me is Dr. Joel Coley. He's a NASA postdoc fellow at Goddard who worked on this research, he's going to tell us his role in it as well. Thanks for joining us, Joel. It's good to see you.
Nice to see you too.
All right, let me start with Robin. You've discovered this thing. It is a binary system of bodies, one of which is a star. The other is this thing that is orbiting around it. We're not quite sure what it is. It could be either a neutron star or a black hole, but you found this periodic brightening in gamma rays of this object. So why don't you describe, first of all, what you saw, and then a little bit about some of the research that you did that followed up.
Yeah, so my main area of focus is studying binary star systems, two stars orbiting around each other, just like the Earth goes around the Sun, for example, except that I study systems which contain what we call a compact object, like you mentioned, a neutron star or a black hole. And these can give off very energetic forms of radiation, like X-rays and gamma rays. But the ones which give off gamma rays are extremely rare. So my job here at Goddard is to work with the Fermi satellite, which is a satellite designed to study gamma rays. Because I think you mentioned we need to go to space to study gamma rays. We have a little figure. I don't know if you want to throw that up again.
Getting it right now.
Okay. Yeah. So as we know, the part of light that we see, the part of the electromagnetic spectrum that we see with our eyes, is only a total tiny sliver. And if we want to study other types of radiation, we quite often need to go to space. For example, gamma rays don't get down to the ground. So the Fermi satellite, this international project I've been working on, it's been in orbit for 8 years, and it's been surveying the entire sky. And I use the data from this to try to look for binary star systems which are giving off gamma rays. These are very rare. I wonder if you want to throw up the sky map from
I'll be more than happy to. I just want to make a couple of comments on this particular graphic here. This is amazing. There's a lot here, folks. I want to make sure you get. First, you see the entire electromagnetic spectrum put in graphic form, and as we mentioned at the top of this, gamma rays are the most energetic form of electromagnetic radiation that we have, and these arrows show how far down in the atmosphere it goes. And look, the radio, we've known for a long time, it goes down to the ground. There's parts of the infrared that do not, which is why we have telescopes like Hubble with infrared cameras, as well as James Webb coming up with infrared cameras, because it doesn't get down to the ground all the way, at least not unless you get very, very high in the air, which is another reason why we have observatories way up on mountaintops. And of course, visible light, we've known, goes all the way to the ground, but ultraviolet, X-rays, gamma rays, all of these things can really only be seen from space. And Hubble is the only game in town right now that can see the ultraviolet, but we also have X-ray telescopes and gamma ray telescopes. And so this is an object that is very bright in the most energetic form of radiation that we can detect. And so I just wanted to kind of back up a little bit and emphasize that there's a lot here that's very interesting, and we're talking about this region of the spectrum, the gamma ray portion. Okay, what did you want me to put up now, Robin?
I was suggesting putting up the map of the entire sky from the Fermi satellite.
Okay, let's see if I can find that real quick. That is the let's see, is it this one? Here we go, the 5-year. This one?
Yeah, probably. So
okay, probably.
In fact, it was. So this is a view of the entire sky. It's like taking the entire surface, sky that we see, and flattening it out, like you do with a globe of the Earth.
Yeah, we have one of these with a cosmic microwave background as well.
Okay, right. And so this is plotted so that we see the bright streak going across the center there, which is the plane of our galaxy. So we see a lot of gamma rays coming from the plane of our galaxy, the Milky Way. And within these gamma ray we detect, we've identified about 3,000 individual sources of gamma rays.
Right. So that's these red dots with white centers. They're very bright. These are all gamma ray sources outside of the plane of the galaxy here.
Yeah, and in fact, there are others buried in the plane of the galaxy as well.
Right, I'm sure. That we can't. That are sort of in the background.
Yeah. So there's actually another image, 3 FGL sources, which shows the.
Make me work here. Okay.
Yeah, sure. Shows the individual sources we've managed to identify from that sky map. So the other one's basically the raw data.
What's the name of it again?
3 FGL_sources. .jpg.
Okay.
Number 3 FGL. So this will just
going.
Show the 3,000 sources we've identified, and among these, what I and my colleagues are interested in doing is trying to identify potential binary star systems, these binary star systems which give off gamma rays. And the way I've been approaching it over the years is by extracting information on each individual source, looking how they vary, then applying a mathematical technique to try to look for periodic variability.
So these are all of the things that NASA's Fermi spacecraft has found as possible sources of X-rays, and they've tried to categorize what they are. Like if it's a little star, it's a pulsar. If it's like this, it's a binary. Now, it's a little bit fuzzy, folks, and I can't control that, but I will tell you that all of these graphics will be made available for download after the Hangout is over, and I'll put a link in the description box below so you can get these yourselves to see them a little clearer. Now, what I am not seeing is a whole lot of these squares with crosses in them. At least I can't see any from this. So that means there's not very many of those.
So can I interrupt for a second?
You may. Go right ahead.
So all of those empty squares, which there are a lot of them on the central plane, those are all things that we don't know what is creating the gamma rays at all. And a huge amount of work has already gone into and needs to continue to go into figuring out what those things are. So
but what about oh, go ahead.
Oh, sorry. So the problem with the Fermi telescope is that it doesn't take very detailed pictures, that the pictures are kind of blurry. So you know there's a gamma ray source there, but you don't know where exactly it is. So you have to be able to figure out what kind of, like, what source the sky, because all you've really done is sort of localize it to a general area, is you have to actually do a lot of homework with other telescopes to figure out what's actually producing the gamma rays.
Okay, so what I'm going to emphasize here is this right here, where you see where it says binary, this is square with a cross, it's red. Is this what we're talking about? Is this the classification that that this paper is about?
Well, yeah, except that at least as much interest to the ones which have no association, i.e. we don't know what they are.
Right, that's this one.
Yeah, so there's a huge, as Laura said, the images we get from gamma ray satellites don't give very precise locations on the sky, which is the reason that, as Laura was alluding to, we need to do, once we find a source, we have to do the follow-up observations, which is what we've done. And it kind of goes back to the image you showed before about the different types of wavelengths and the different types of observations we can get. So on our team there, but maybe I should backtrack to our discovery, and then we can continue on to the
yes, I want to
follow-ups we did.
So I was just going to say, it's like the imperfect analogy that I think about. It's like, you know, when your fire alarm's battery is going dead and it chirps and you can't figure out where it is, which one it is. It's like that. It's like, is it this one? So you have to follow up the observation.
That is so annoying when that starts to do that.
Else. It's like, I hear it. Well, which one? Is it the one in the kitchen or is it the one in the living room? Anyway, it's like that. You don't know right away which one it is, and then you have to, of course, follow up. So you have a general idea in the sky, but that's why we need other kinds of telescopes to pinpoint these objects.
And before we leave this graph, I just want to so from my reading of this, the vast majority of these are these blue X's, active galactic AGNs, or active galactic nuclei. Is that right? Now these are things that are happening. These are gamma ray bursts, correct?
No,
they're active. They're always shining in gamma rays.
They're variable. These come from the supermassive black holes, which are found in the center of all galaxies. In this case, these are so-called active galaxies, which are giving out huge amounts of energy. And they have beams which are coming out from that. And if the beam is pointed towards us, so-called blazar, then we're most likely to see those in the gamma rays. Now, as somebody who mainly works on binary stars, I find them a nuisance and a kind of noise.
I can see why. There's a lot of them. Yeah.
but of course, they're highly important scientifically, and other people regard them as, you know, some of the most important things we're doing, and they're extremely intriguing, coming from these billions solar mass black holes. So these are amazing objects. You notice that you find them all over the sky, whereas with the stars, the binary star systems, in general, we expected those to be found inside our own Milky Way galaxy, and you'd expect those to be located in the plane of the galaxy, except for the one that we found recently now, the subject of our paper, which was a big surprise.
Okay. Yes. So before, okay. So everything on the blue stuff, the red, the blue X's are probably, well, almost certainly if they're active AGNs, outside of our galaxy, while the other things, the red stars, the red squares, those are things happening inside our galaxy. Is that safe to say for the most part?
Yep.
Okay, so and now let's get to where. So, and you're right. Most of them appear to be along the plane of the galaxy. Although, as we pointed out, it may be difficult to differentiate individual sources from the background of the plane of the galaxy. But there are clearly things that are way up out of over the plane of the galaxy, and in particular, this discovery, and this is where I'm going to get you in, Malcolm, because you want to talk about this, and I want to too. This particular discovery, this particular object, LMC P3, is called that because it was found not in our galaxy, but in the Large Magellanic Cloud. So why don't you tell us a little bit about what the Large Magellanic Cloud is and what's so great about it?
Okay, my favorite topic. I can talk for hours on this.
That's right.
Can we start off by putting up the picture called Magellanic Clouds?
Yeah, just for reference. Just for reference, I just screen shared the visible light image of the Milky Way, and you can see the Magellanic Clouds down to the southern
I love that
portion.
photo. That's an awesome picture.
So that's visible light. Looks very different than the gamma ray light, and then you're going to see a close up in 1 second of the Magellanic Clouds. A much better picture. Just context.
It's that thing in the
lower, the whole sky.
Lower right. Yeah. There you go. Pointed out. There you go. Okay, good.
Okay.
So that's where we're talking now. That's where this gamma ray binary was found. And Malcolm, here's the picture you wanted me to put up. It's now big.
So I think following on from everything that just Robin has been saying, and you were saying that, we're finding what Magellanic Clouds live way off the plane of our galaxy, off the Milky Way. So we immediately know that they are probably separate entities from our own galaxy. And the great thing about the Magellanic Clouds is they're our nearest galaxies that we can go out and study and see how stars are living their lives in an environment which is quite different from our own Milky Way. And the key thing here is what the astronomers call the metallicity. It's essentially
we've talked about that.
A measure of the composition of the elements in these Magellanic Clouds is very different from the Milky Way. And the composition is very primitive. It's similar to very early galaxies, we think. And so what that's telling us is that even though we look at them now and we see lots of stars shining in these Milky Way, millions of stars shining in the Magellanic Clouds, they can't have been doing it for the whole age of the universe. They must have switched on relatively recently, because otherwise we'd have a different elemental composition in the Magellanic Clouds than we find.
So based on what these stars are made of, which you're finding are more or less very similar to each other, tells us a lot about how long they would have shined, how long these galaxies.
Yeah, in fact, all the stars that we're talking about, these gamma ray binaries and the other kind of X-ray binaries, are all short-lived phenomena on the scale of a galaxy. They live typically for only 10 million years, something like that. Whereas, that's factors of 1,000 down on the age of the universe, or the age of our own galaxy. So we know that because massive stars live very short lives, that's the intrinsic nature of the beast. And so by finding all these massive stars and the products of all these massive stars, the neutron stars, the black holes, is telling us that something really dramatic has happened in the recent lifetime of these two objects that is totally changing the way they behave. And what we think the answer to that is tidal interaction. So we think these two guys are kind of tidally interacting with each other in such a dramatic way that they're kicking up a whole generation of new stars. And the reason we find so many X-ray emitting neutron stars and black hole systems is the consequence of all these huge stars being born. But in relatively recent times, it's all a relatively new active region of star formation that we're looking at here.
I just wanted to point out the very clever name that the astronomers have given these two objects. They're named for Magellan, who noted them when traveling in the south, and they are called the Large Magellanic Cloud and the Small Magellanic.
Yeah, I'm no astronomer, but I'm going to go out on a limb and say this one is the large one, and this one is the small one.
It avoids confusion. There's no confusion.
You would be right.
They do look like clouds, though, even in this high definition photo. They do look like clouds, but this is a galaxy, folks. These are satellite galaxies around very close to our own Milky Way. So,
and the clouds comes from John Herschel, who observed them back in 1820, 1830, and produced the first images that we have of these. In fact, the images were his drawings of them through the telescope, but they're our first visualizations of the Magellanic Clouds, and he called them clouds because, you know, at first glance, when you look up in the sky, they look a bit like they could be clouds floating across the sky, but they're not. And what I feel really sad about is that I live in the Northern Hemisphere, and I can't go out of my back door and see these.
I know. I remember the first time I went to Chile, I was amazed at what I could. It was beautiful.
They really are quite special for the southern sky.
Definitely true. Okay, so there you go. There's a background on the two satellite galaxies around our Milky Way, the Large and the Small Magellanic Clouds. Very interesting objects, and we're not done talking about what's in them yet. But I want to take a moment and remind everybody we're having the Astro Coffee Hangout, and we are talking about a unique gamma ray binary star system that was located in the Large Magellanic Cloud by our team that's here with us today. And we're talking about what these things are and what gamma rays are and things like that. And my guests are Dr. Robin Corbet, Dr. Malcolm Coe, Dr. Laura Chomiuk, and Dr. Joel Coley, from the papers that we're talking about now. So, all right, so let's go back. So, Joel, I need to get you into this. I realize that. I'm sorry that you're sitting there, but before I want to talk about your observations, but I have to get Robin to say that let the groundwork for this discovery, gamma rays, and NASA's Fermi Space Telescope looked, and you saw a periodicity coming from the Large Magellanic Cloud.
Yeah, so as I mentioned, I've been looking at every single one of these Fermi sources. My computer crunches away, keeping my office warm, running for weeks on end. And I use a technique called the Fourier Transform, based on something invented by a French mathematician. And it's actually analogous to how our ears work. So when you listen to a sound, that the note, say played by a flute or a musical instrument, you hear a particular pitch. You don't notice the overall variability, but you hear the pitch standing out. And our ears are basically working in a similar way to doing Fourier analysis. So what I do with the gamma ray data is I do a Fourier analysis of the light, what we call the light curves, the variability, and I look for something which kind of stands out as a peak in the graph we get that way. And that's kind of the equivalent of a pure tone. But whereas the note, musical note, shows something which is changing hundreds of times per second, in this case, the signal I saw from the Fourier transform, this particular gamma ray source, was something changing every 10 days. And we expect in many of these systems that the gamma ray emission will change as the two stars orbit around each other. And yeah, this is the graph here. So the strongest point in that graph is showing the equivalent of as hearing a note played on the piano or guitar or whatever.
That's this line right here.
Yeah, that's right.
Okay.
And the dashed line shows that it's statistically significant with a chance of getting that by probability of getting that just by random fluctuations of it's more significant than 99.9999. I can't read that number of lines there.
Basically, this is pretty real, is what you're saying.
So there was actually another step involved along the way, which brought it out to be so strong there. We saw something which was pretty strong, and then actually due to some work from some French colleagues who are also on the paper, enabled that to be refined to be even more incredibly strong. There's another blip, the second highest one peak there. That's actually not not a real thing that's at a period of 1 day, and it's just due to the way the satellite goes through the radiation belts around the Earth. So I often see these things which are not real, which are kind of tantalizing, then you realize they're not real, so it's frustrating. But in this rare case, so I said we were crunching through all this data, all these thousands of sources, and I was hoping to find another new binary to add to the handful we already knew about. But the strange thing was that it didn't lie on the plane of the Milky Way. Instead, it was lying in the Large Magellanic Cloud, as we were just talking about. And so this was quite stunning. But the thing is, we wanted to figure out where it was actually coming from on the sky. Laura mentioned we don't have a very accurate position from the gamma rays, so it could have been quite a wide variety of places there. So at that stage, when the rest of the team started to become more heavily involved, and we wanted to do the observations at a variety of different wavelengths. And probably the next step in the energy was to do the X-ray data. So X-ray emission is rare, not quite as rare from the gamma rays. So we already knew about a source of X-rays kind of within the blurry field of view of the gamma rays. And we wanted to see whether this could possibly be the X-ray source. So we got data with the Swift satellite, which maybe you want to have Joel.
Okay, yeah, I will. Okay, that's good. That's a good segue.
Yep.
But before I put this graph down, I'm going to try and do my best here, but I want to iterate that if you have a set of data and if you do Fourier analysis on it, as Robin mentioned, you get, and if there is any periodicity in that data at all, in other words, things that go around each other, or if there's anything that repeats itself, it comes up like this. This is a spectrum. And you can see as the frequency is along the bottom. So all of the things in that data that would have had some kind of periodicity to it show up in this thing called a power spectrum. And this peak right here was very strong and very powerful. You could not see this if you just looked at the data itself. You had to do what Robin mentioned, which is a Fourier analysis, and get this picture. So that's what this is, and it's an incredibly powerful technique in astronomy for finding things that repeat themselves in both images and like a lot of times if you have a wavy pattern in data or just noise in data, it's a good way to help identify and remove some of it if it is periodic in nature. So, okay, we looked at the gamma rays. You did a good job of finding things there, but you said, okay, we can see it really well. We can see it really well here in this part of the spectrum in gamma rays. Now let's move down. Let's move down and let's see what we see down here in the X-rays. And Joel, I believe that was where you come in, right?
Absolutely. That's exactly where I came in. So what we ended up doing was we looked at the source with the Swift telescope, or we specifically looked at the Swift X-ray telescope studying the sky between 0.3 to 10 keV. And this is co-aligned with the ultraviolet optical telescope, as you can see here, one of 3 instruments on board Swift. So the one thing that I was thinking that could be excellent for show the audience would be the figures with the gamma ray light curve, the X-ray light curve, as well as the radio light curve.
Okay, can you give me an idea of what that would be called? Is it this one, multifold?
It should be multifold.
Yeah,
yes.
Okay. I got it right. Woohoo!
Perfect.
Let me drive the internet. Okay, go ahead.
Okay, so we studied the source with the X-ray telescope, and specifically, as Robin alluded, our source is in fact embedded inside a supernova remnant called DML241. And the X-ray telescope studies the sky between around 0.3 to 10 keV, but because it was embedded in a supernova remnant, in order to get the signal from the noise, I actually looked at specifically 2 to 10 keV. In fact, LMC P3 was noted before. It was initially thought to be a pulsar wind nebula and sourced by Bamba et al. 2006. I can give the link to that paper. Studied the source with XMM Newton, and then later on, Seward et al. In 2012 studied the source with Chandra, and they thought it was an X-ray binary. So we wanted to look for the 10.3-day orbital modulation in the X-ray. And what we just looked at were folded light curves, one in the gamma ray on the bottom, one in the X-ray in the middle, and in the radio. And one thing that I wanted to allude to was the fact that the X-ray maximum is occurring at gamma ray minimum, and gamma ray max is occurring at X-ray minimum.
Yeah, let me just pause you here. I want to go back over that. So here at the bottom panel, gamma rays. This is what they saw in Fermi.
Yes.
Right, the panel right above this is
It's
X-rays.
Swift.
It is what Swift saw, but as you just said, when it gets low, the other one, the gamma rays get high. Is that the way this always works in these two wavelengths?
In many of these systems, yes. Another such system is LS5039, which is
Oh yeah, my old job. Sorry.
which is a source just about a couple kiloparsecs away, and it shows the exact same type of behavior, where in the X-rays, this occurs at inferior conjunction, or when the compact object is between us as well as the donor star. In our case, we're looking at an O-type star, which is much more luminous than the sun, and its
we
lifetime.
need to put that animation up to show what you're talking about. But as things are going around another star, this is what you're talking about.
Exactly.
Depending on that orientation, you may or may not get this phase difference. This is called a phase difference, folks. When
Yes,
this is doing one thing and this is doing the exact opposite 90 degrees apart, that's a phase offset.
So just to be clear, so Joel, the second source that you mentioned, is that actually in our galaxy then? So we have an
LS5039 is in our galaxy.
in our own galaxy. So, and we knew a lot about it before. I mean, did we know about that source before? So we said, hey, oh, this one might be similar.
Actually, LS5039 has been studied for quite some time, and it was confirmed with Fermi. So.
Okay.
Yes.
So you sort of
As
had
well as-
handle your hands around that, and then you see this similar phenomenon, and think, maybe it's similar.
Right.
Okay,
But,
so
one thing that's quite intriguing that I wanted to allude to with LMC P3 is it's 10 times more luminous than LS5039, as well as other gamma ray binaries in the X-ray, as well as the radio. And as Robin was talking about with the gamma ray, it's about 4 times more luminous.
Wow.
So not only of the 5 of these that we know about, which are very rare, this one's one of the brightest.
Mm-hmm.
Yes.
Yeah.
Okay.
And which is one of the reasons which it allowed us to find it in the LMC. If it had been fainter, it would be much harder to discover it.
Also, these could be going on a lot more but they might just be dimmer, and our instrumentation can't find it yet.
That's a big question, actually. It's been predicted that there should be like several tens of these, maybe 20, 30, something like that, inside our own galaxy. But so far, we've only found a fraction of that number. And one of the motivations as we get more and more data is to dig deeper and deeper to try to find them. And so I was surprised. I found one. So the only completely new one found was Fermi. We had some hints before. So 6 years ago, I found one inside our own galaxy. And after finding that, I expected to find a lot more. But instead, it took another 4 or 5 years.
So these might just be inherently rare things. I mean, these are...
it may be the models which predicted the lifetime. So we think that after there being gamma ray binaries, they're going to evolve and change to become X-ray binaries. And so based on the X-ray binary we see now, the suspicion was we would see more of the gamma ray binaries. But perhaps our model's wrong. Maybe they live for shorter periods of time. Maybe the neutron stars inside them are born with different spin periods and so on, rotation periods. So this is telling us quite a few things about how stars are born and die, about how they interact together, how gamma rays are produced. It tells us about what's going on forming stars inside the Magellanic clouds, as Malcolm's talking about. So this one particular system can bear on quite a variety of different issues.
Right.
I think it's worth just emphasizing what Robin's saying here. He's basically saying they're not necessarily rare objects, but maybe they only live for a very short amount of time in the phase in which we see them as gamma ray binaries.
That makes sense, yeah.
And so it's a statistical thing. You know, there may be lots out there, but if they only live for a short time, then the chance of us finding them is much reduced.
Yeah, that makes sense. Okay, well, before I need to move along because I want to get to the actual animations of what you guys are finding and what this thing looks like. But right now we're talking about the data that you took and the way in which this alerted you to its presence. And so either Joel or Robin, one of you can comment on this top panel here. This is radio data. It seems to more or less go along with the X-ray data, but maybe you guys can explain what the blue squares and the red dots are.
So this is radio data taken at 2 different frequencies. So this was done by our friends and colleagues down in Australia, also contributed to the paper in a big way. And having the radio emission coming from this binary star system was also a sign of it being unusual and exciting. So even before we saw the fact that the radio was changing in the same way on the 10-day period, when we first knew it was giving off radios, that was a sign of something different and exciting going on there. Normally, the cousins of gamma ray binaries, which are the X-ray binaries, they're not usually so dramatic in the radio. So that was another clue that this was doing something dramatic here, something interesting. And you see, the radio and the X-ray follow each other, which we think is tied into the physics of how these gamma rays are produced.
Okay, so going back to this, we're seeing that this is very bright in gamma rays. We're also seeing that the data we have are in X-rays, and now with 2 different frequencies down here also show a very bright periodicity going on in the data. So that's your data. You said, aha, this is happening in the large Magellanic Cloud. And Joel made a comment, I'm sorry, Malcolm made a comment before we started that it's no accident that we saw this in the LMC, but I want to get to that in a minute after we show this animation about what you think is going on with this system. So I'm going to go ahead and put it up, and then maybe, Robin, you could go ahead and give us a little, here it is, bit of maybe a narration of it as it goes along. So this is what you think is happening. We have a star right here. This is the 20 to 40 mass regular ordinary star, and this other thing going around it. It's purple. You want to comment, someone? You're muted.
Yep, sorry. Yeah, so this is showing the Magellanic Clouds, these other tiny galaxies that we know about. Now we're kind of zooming through the image. We're coming across this supernova remnant. So it's another thing that so this is a star exploded and left behind this remnant. And we think that the purple thing here indicates the source of the gamma rays. This is an artist's impression. This neutron star or black hole formed in a supernova explosion going around this young hot star, this 2030 solar mass star there. And
I paused it real quick for this. Mm-hmm. Yeah, and so here are the other systems that in our own galaxy, but this one, as we talked about, is not in our galaxy. There it is, right there. So there is where LMC 3P is, or P3. Okay, well, this is good. So this is what I think is going on now. We see this thing going around, but one of the things that's not clear, and I talked about this a little bit with Laura before we got started, but it's possible that because we don't fully understand, we don't fully understand this plane of rotation, do we, Laura?
Maybe Laura wants to comment.
Oh, I keep doing that. What? Yeah. What? Did you hear me?
Yes.
Okay.
Yeah,
okay.
And obviously, so another key thing is the data that Laura and her colleague obtained, which basically derived the orbit there that she's going to talk about. Sorry, didn't.
Okay. Go ahead.
Yeah.
Yeah. So tell us a little bit about this orbit and what we do and don't know about it.
Right. So basically, we know that there's something about this star system that is creating high energy radiation. And there's something about this system that repeats every 10 days, right? Because we see this periodicity. And so astronomers always, by default, when we look at a star and if we see a periodicity, we usually assume it's a binary star, right? There are 2 binary stars orbiting around one another. And the problem is that if you look in the optical light, you see a star, you see that blue star, and that blue star is very bright and very dominant. And it looks like a massive star, very hot, very blue. But we know that if there was just a massive star there, it wouldn't be creating all this high energy emission, and there wouldn't be this fluctuation every 10 days. So there must be something else in the system screwing with us, right? That's leading to some kind of energetic interaction, and it's also, right, doing something every 10 days. So though, whenever astronomers see something really energetic, we usually assume it's either, the best way to get really energetic phenomena is to have really strong gravity in the system. And the way to get good strong gravity is to have a compact object like a neutron star or a black hole. So we really want to know what that mystery object that's orbiting around the blue star is. And the way we can do that is by basically measuring the blue star as a function of time over the course of its orbit and seeing if it wobbles back and forth. And if it wobbles back and forth, it does indeed mean that there's something traveling around it, orbiting around it. And you can figure out the relative masses of these two objects.
Just like we do exoplanets, folks, with radial velocity. Just so I put that.
It's exactly like exoplanets. And so, and we think we already know, right, the mass of the big blue massive star, because it's hot and it looks like other massive stars that we've studied well. So we think we know the mass of the blue star, and we think we can get the relative masses of these two companions by figuring out how fast the blue star wobbles back and forth. And so we can figure out the mass of this mysterious dark companion. We can figure out more about why it is messing with this poor massive blue star so much. So we saw the wobbles. So basically, I have a lot of time, very graciously, purchased by Michigan State on this telescope in Chile called SOAR. Do you want to show us SOAR?
Okay, sure. I'll bring that up.
The SOAR telescope.png.
It's
so
beautiful.
it's a nice optical telescope. It has a 4-meter mirror. So this is a nice medium-sized telescope, and it's in Chile. But I am blessed to have a remote observing room here at Michigan State. So I just go downstairs and
yeah, but nothing substitutes
stairs.
for going out there and looking up. I'm just saying.
Yes, but nothing also substitutes for being able to sleep in your own bed sometimes, right? Having the option.
Fair enough.
Very valuable.
Fair enough. Okay.
And especially for this kind of observations where we really wanted observations every night, right? This is a 10-day period. You want to know how the star is changing over its period. So ideally you would be there and observing every night for at least 10 nights. So it's really lovely to just be able to run downstairs. So I used this telescope in Chile, and we observed the hot blue star that we could see, and we did indeed see it wobbling back and forth.
So that told you that there was something in orbit around it, okay? Coupled with the SWIFT data and the Fermi data, all of this is coming together now. So now you're seeing a wobble. You're seeing these periodicities and these other wavelengths, radio and X-rays and gamma rays. And now you're going with an optical telescope and saying, hey, guess what? This thing is wobbling.
Right. So it does. Everything is coming together, right, to imply that there's a mystery companion that's screwing with the hot blue star and creating all this energetic emission. And the most likely culprit is a neutron star.
A neutron star. Now, these are remnants. These are stellar remnants of a supernova explosion, correct? This is what's often left behind from a supernova.
Yes. Does somebody else want to explain what neutron stars? You want me to do it?
Well, who wants to go? Hey, Joel, you want to tell us about neutron stars?
Sure. So neutron stars are the endpoint of stars, generally 8 solar masses or above, and these are compact objects about 1.5 times the mass of the sun, packed in something as small as, say, Washington, D.C., about 10 to 20 kilometers or so.
And every bit as dense as Washington, D.C., sorry.
Actually, far, far more dense, on the order of
hard to imagine.
You've driven in Washington, D.C., I'm sorry.
At a meter cubed or so. So what's amazing about these is they're entirely composed of neutrons. So what happened was we have neutron degeneracy pressure pushing outward, and we have gravity pushing inward. And it's in what we would call a hydrostatic equilibrium between neutron degeneracy pressure, or the neutrons, there's something called the Pauli exclusion principle, where no two fermions can exist in the same state. A neutron is a fermion, a spin of 1/2 or minus 1/2.
Right. So that, yeah, that's a little more than I want to go into. We just want to say these are incredibly dense, primarily made of neutrons, and because of the Pauli exclusion principle, they can't be in the same place at the same time, and so they are very, very tightly packed. And so, okay, so it could be that in orbit around the star, but it might also be a black hole. Is that right, Laura?
Yes. So and
now, why don't you know which one it is?
So because both neutron stars and black holes have very strong gravity and are quite dark. Neither one of them is very good at creating their own light.
Okay,
right?
So we don't know, but we don't know for sure which one it is, but it could be still a black hole. A lot of it, I think from the paper I read, said that it was dependent a lot on the orientation of the orbit. If we knew that orientation better, we might be able to say whether it's one of the two, correct?
Right. So the way the astronomers usually work this is if it looks like it's really strong gravitational pull and it's dark and it's less than, say, 3 times the mass of our sun, we say it's a neutron star. And then if it's like 5 times the mass of our sun or greater, we say it's a black hole.
Okay, I'm sorry to rush you, but I'm running out of time and I want to make sure I get this. You got this from the wobble, right? You got the mass from the wobble.
You get the mass from the wobble,
okay,
but what
great.
mass you calculate depends on what inclination you assume for the orbit.
Okay, great. So that's why we still need to we need to get a further handle on this inclination. Now, if it's a neutron star, which currently you guys are thinking it is, it's most likely. Malcolm, you said earlier in the before we started actually, and I want to get your comments on it. There's no accident that we saw this in the LMC. This is a good reason for finding this in the LMC. Can you elaborate on what you meant by that?
Sure, very happy to do that. I think the key thing we've learned about the Magellanic clouds is that because of all this interaction I was talking about earlier, the tidal interaction between these two guys, there's been a huge triggering of star formation. And the consequence of making lots and lots of stars, especially lots of very massive stars, as Joel was indicating, is that you end up producing lots of neutron stars and black holes potentially all over the place. Now, before we started, we went online. You actually asked a question, which I think is interesting.
I know. I don't know if I have a chance to get to it now, but okay. I'll ask my question is: how can you have a neutron star or a black hole as a companion if those are the remnants of a supernova? Could a star have survived a supernova, or was it captured later after it occurred?
Right. So capturing later is a very rare phenomenon. It might possibly happen in the center of like a globular cluster where the stellar densities are incredibly high. But in the normal sort of space of the Magellanic clouds, the probability of capture is very low indeed. So we have to assume that what we're seeing did actually survive the most violent explosion that a star can undergo, and somehow still hung in there as a binary partner to the other star.
A 20 to 40 solar mass black hole, or star, I mean, can survive?
No, sure, why not? I mean, it just gets a bit of a
why
blast.
Not? Sure.
You know, I think what's the bigger danger is that if the explosion that makes the neutron star or the black hole is even slightly asymmetric, then it's going to kick this neutron star out of the binary system. And so you want an almost beautifully perfect symmetric explosion that keeps the neutron star sort of in place and doesn't actually give it a huge kick and break up the binary. So it's quite probable, and I believe it's very likely, that there must be lots more of these guys around.
That's amazing. I'm sorry, Malcolm.
It just blew the whole thing apart. And so we got neutron stars and black holes wandering around on their own, filling through the Magellanic.
Unsupervised.
Yeah.
Unsupervised, yes. Uncontrolled, just minding their own business and not causing any problems for anybody. So the ones we see are just the subset, the few guys that have survived this very violent process.
By a random sort of, because it was a symmetric explosion, it managed to stay intact. That 40 solar mass star managed to stay alive.
And so what's going to happen next is the 40 solar mass star is then going to go through this whole process and blow itself up, and again almost certainly going to split the binary up. But if it doesn't, we end up with this very rare phenomenon of 2 neutron stars or 2 black holes going around each other. And this could take the whole story off into gravitational waves.
That's right. So now you know how you can have 2 gravitational waves or 2 black holes interacting.
that's a nice scenario, yeah.
And that would eventually become a gamma ray burst if the two neutron stars eventually merge together.
I would love to get into gamma ray bursts too, but we are totally running out of things, running out of time, and I got to get to some questions. Okay, so the large Magellanic Cloud, turns out it's basically, as Malcolm said, a huge nest of neutron stars. There's lots of things there, so that's one of the reasons why seeing it there is not a surprise to anybody. Let me get to some of your comments. You guys are going nuts on the chat here, and I want to. George Caldwell is doing really well here, and he's asking, do we ever see gamma ray activity from globular clusters, which may indicate black hole activity? Carol, this is about on your thing, globular clusters. So do we ever see gamma ray activity in globular clusters?
Yeah, yes, but the environment is different, as we were speaking about before, because globular clusters are more complicated because there are so many stars in them. Some of them are quite compact. And also, I'm not so sure, I mean, this object is in near the tarantula, right, in the LMC. It's a different environment. Tarantula is not making a globular cluster. And so it's not clear in the center of a globular cluster whether stars this massive and binary systems would even be made or survive. So I think it might be a little different.
Yeah. So if I could comment.
Sure, please.
We do see gamma rays coming from globular clusters, but these tend not to be these young type of stellar systems. Malcolm mentioned they only live for a few million years. As astronomers, we say only a few million. Globular clusters are much, much older, billions of years, but the early massive stars there may have exploded supernovas, left behind neutron stars, and if some of them turn into millisecond pulsars, a particular type of very fast rotating neutron star, they can make gamma rays in a different way. So the gamma ray emission from a number of pulsars in globular clusters has been seen. So they're similar in the fact they contain neutron stars, but the way they got there is more complicated and different.
And actually in your map, there were a number of pulsars that noted that are not necessarily binaries.
Yeah, that's right. These would probably be binary star systems. Well, some of them were just single. The very fast ones went through a phase of having a binary companion which got evaporated away. So two of the main things we see are these active galaxies with Fermi, and we also see lots of the pulsars with or without companions, or having had companions in the past.
Good. Okay. This is a good question. It kind of goes on to mine that I asked Malcolm. George Caldwell's also asking, wouldn't a supernova occurring near a star cause a nova in the other star? I mean, I'm sorry, Malcolm. I'm having a hard time with this. If you have a supernova occurring right next to another star, that star is just not going to be what it was before, right? Something had to have happened to it. Is that?
So I think both stars have evolved and changed over their lifetime. There's a lot of mass transfer taking place between these two stars throughout their whole lifetime. So neither star is what it was to begin with. They both have changed substantially. And it's this transfer of matter backwards and forwards over the lifetime of the binary that eventually gets one of them into a state where it just explodes.
Okay.
And so I think, we're a long way away from original stars now. The whole things have evolved in a very complicated way.
Sounds like there's two stars orbiting each other who can't stand each other, just making each other's lives miserable. And finally, one of them just says, fine, I'm blowing up. Boom, off it goes. And the other one goes, oh, wow, that was big. Okay, now I've got a neutron star. Well, that's irritating. I'm going to blow up now. Boom, and I'm done. And then the whole thing goes off. So this is a picture I did not expect to see. But
it's not a very good relationship.
It's very destructive.
Yeah, and I think I think the question was asking about nova. Mentioned nova.
Yes, nova. Yes.
Where there's something completely different involving a white dwarf, which is.
That's correct. Novae are the material that come off and are drawn onto a white dwarf star, reaches a certain point and it flashes, and it does this periodically. So yes, it's not a supernova, but. Or a hypernova either, which is a different topic altogether. Okay, so I guess we will. I want to go ahead and start wrapping it up, but I want to just touch base with you guys. Is there anything that we didn't cover that you think we should have? You guys have been studying this system, LMC P3, for a while in a variety of wavelengths. Very massive. Is there any way these gamma rays are going to adversely affect us? I should just ask that. It's in the Large Magellanic Cloud. How far away is it?
It's a long way.
Okay, can we?
About
150,000 light years.
150,000 light years.
Yeah. I don't think we should worry about that particularly.
Okay. All right. Fair enough. Okay, good. So the gamma rays from this thing probably aren't going to be much of a factor here.
No, I mean, we had to fight hard to find them, and so they're not, they're not completely. So anything that goes off in the Magellanic Clouds, it's great to look at, but they're not close enough to threaten life on our planet. If that's really where you're going with this.
Yeah, I think we're only getting like an average of 1 gamma ray per day hitting the spacecraft. Maybe up by a factor of 7 there, but it's such a small number of gamma ray photons. That's why it's so hard to find them.
It's worse than your smoke alarm. It only chirps once a day.
So nowhere near as annoying. That's good to know. Okay. All right. So what's next for you guys? We got a couple minutes here. Have you guys comment just very briefly? Are you guys gonna work together on finding more of these? What's going on? What's going next?
Well, from my point of view, I'm continuing to churn through the data as we get more and more gamma rays, trying to find more of them. Have a couple of little hints from other ones, not sure whether they're going to be real or not. And then in terms of this one now, there's still a lot more to follow up, measuring the orbit better, measuring the X-rays better. So lots of the people on the team are continuing to do observations of this one as well. I don't know if anybody else would like to comment on that.
Yeah. How about you, Malcolm? Go ahead.
Yeah, no, I'd just like to say that we've kind of overlooked the really interesting guy in the pair of this, which is the Small Magellanic Cloud in this story. The Small Magellanic Cloud has many, many more neutron stars and black holes than the big guy. And so if I was a betting guy, which I kind of am on a good day, I'd almost put a pint of good British beer on the fact that we're going to find one in the Small Magellanic Cloud next, because a lot of guys there waiting to be discovered.
Okay, great. Okay, Laura, what are you guys continuing to go through your data sets, the radio and the optical stuff on this, or are you guys looking into more of these gamma ray systems?
Yeah, so we're trying to turn some of those gray squares into colors, right? We'd really like to know what these unidentified Fermi sources are, and a lot of that is just following up with other wavelengths.
Great. Well, may all your gray squares turn into color squares then. I hope that goes well. Okay. And Joel, how about you? What are you still working on more, finding out more of these things, or you moved on to the X-ray world?
One thing that I'm thinking that could be really cool is further X-ray follow-up. For instance, NuSTAR, as an example, studies X-rays all the way up through 79 keV. So that's an idea as far as being able to understand the physics, what's going on.
NuSTAR is NASA's another X-ray telescope, correct?
It is.
Yes.
Studies the sky between 3 to 79 keV. Another one, which is a European space telescope, is XMM Newton. And that could really help us understand the physics better as well.
Does Chandra help you much in your work?
Chandra has, in fact, Seward et al. From 2012, that was a Chandra study, and they postulated it to be a high mass X-ray binary. And with Swift, we studied the source and found it to be indeed the counterpart to Robin's discovery.
Chandra has been up there forever. I wonder how much longer that one's going to be around. That is a really been successful mission. That's
I think the lifetime is still supposed to be quite long.
Yeah, it's an amazing telescope in the sense that the way it focuses the X-rays. And NuSTAR is one of the newer generations of X-ray telescopes. So yeah, that's really great. Well, thank you folks very much. I want to thank all of my guests for taking time out to talk about this LMC P3, a gamma ray binary system where one of the objects is a 20 to 40 solar mass star. The other one is either a neutron star, probably, or maybe a black hole that periodically lets off gamma rays, the most energetic wavelength in the electromagnetic spectrum. Very interesting place to look, and it's a brand new, well, not brand new, but it's a very interesting area of science that is very difficult to measure. So I want to thank all of you guys for your work, and this is Dr. Robin Corbet, Professor Malcolm Coe, Dr. Laura Chomiuk, and Dr. Joel Coley, from all of you guys from NASA, from Michigan State, and from the University of Southampton, for taking time out to talk to us about this great thing. We hope you'll come back.
Thank you very much.
Thank
Yeah,
you.
absolutely.
If you find new stuff, we hope you'll come back. All right. Well, Carol, all right. We did another one. Another Astro Coffee.
Very interesting. Thank you so much for your time. We really appreciate it.
That's right. And I hope you guys will hang in for next week. We have a Future in Space Hangout where I am talking with the members of the Planets Foundation, which is a group they're based out of Hawaii, but their whole goal is to build this gigantic ground-based telescope in the hopes that they can search for life. And we'll have those guys on board in our Future in Space Hangout next week, 3 o'clock on Thursday. So we hope you guys can make it. Thank you all so much for watching. Carol, thank you for putting all of this together and making everything else. I want to thank the American Astronomical Society and the American Astronautical Society for endorsing these Hangouts. I thank you very much for that support as well. So, thank you all for watching. And as always,
keep looking up.